Hi, I'm Ashar Shahid, and this video will explain computer architecture and how high-level programming connects to assembly language and machine code. How information becomes bits. Everything you see on a computer, letters, numbers, images, videos, is ultimately represented as bits, ones and zeros. For example, the letter A is stored as 0, 1, 0, 0, 0, 0, 0, 1 in binary, and the number 42 is 0, 0, 1, 0, 1, 0, 1, 0. This is because computer hardware works with electrical signals that are either on or off, high or low voltage. Through binary representation, we can encode any information, text, numbers, colors, sounds, into patterns of ones and zeros that computers can process. This concept of representing information as bits is the foundation of everything computers do. Boolean algebra and computer logic. Computers make decisions using Boolean algebra, which works with true and false values, represented as 1 and 0. Hardware components called logic gates perform basic operations. AND gates output 1 only if both inputs are 1. OR gates output 1 if at least one input is 1. And NOT gates flip the input. These simple gates combine to create complex circuits that can do arithmetic, compare values, and make decisions. Everything the CPU does, from adding numbers to running programs, comes down to billions of these logic operations happening every second. The CPU and instruction sets. The CPU is built around an instruction set architecture, or ISA, which defines all the operations it can perform. The CPU follows the fetch, decode, execute cycle. It fetches an instruction from memory, decodes what operation to perform, and executes it using the ALU and registers. Registers are tiny, lightning-fast storage locations inside the CPU that hold data being actively processed. The control unit orchestrates this entire process, managing the flow of data between the memory, registers, and the ALU. Different processors use different ISAs. Our course focuses on MIPs, which is a RISC architecture known for its simple, efficient instruction set that's great for learning how processors actually work. Assembly language. Assembly language is the lowest level of programming that humans can reasonably read and write. This course, we learned MIPS assembly, which uses simple instructions like add to add two registers, LW to load a word from memory, and SW to store a word to memory. Each assembly instruction corresponds directly to one machine instruction, a specific pattern of bits the CPU understands. Assembly gives us precise control over the hardware, showing us exactly what the processor does at each step. It is much more detailed than high-level languages like Python or Java, but it reveals how computers actually execute problems. From high-level code to machine code. Here's how here's how high-level programming connects to the hardware. When you write code in a language like C, a compiler translates it into assembly language. For example, the C statement x equals a plus b becomes an MIPS add instruction. Then an assembler converts the assembly instruction into pure machine code, a 32-bit binary number that the CPU can directly execute. This translation processes shows the layered architecture of computing. Programmers write in languages humans understand, which get compiled into assembly that's closer to the hardware, which finally becomes binary that the processor executes. Understanding this mapping is crucial for writing efficient code and understanding computer performance. Memory hierarchy and von Neumann architecture. Modern computers follow the von Neumann architecture, where the CPU, memory, and input/output devices communicate through buses, pathways that transfer data. Memory is organized Memory is organized hierarchy for speed and efficiency. Registers in the CPU are fastest but smallest. Cake memory stores frequently used data. RAM holds active programs and data. And storage devices like SSDs hold everything permanently. The CPU constantly moves data up and down this hierarchy, trying to keep the most important information in the fastest memory. Understanding this hierarchy explains why some operations are faster than others and how programs interact with hardware. Putting together computer organization. You write code in a high-level language which gets compiled to assembly languages like MIPS. The assembly then converted to machine code, binary instructions. The CPU fetches these instructions from memory, decodes them from its control unit, and executes them using the ALU registers and pulling data from the memory hierarchy as needed. Through billions of these simple operations per second, computers run everything from web browsers to video games. This multi-level organization, from high-level code down to transistors switching on and off, is the essence of computer architecture. It's the credits. Thank you for watching. This video was created by me, Ashar Shahid, for Computer Science 3 at Chaffey College.